Okay, cool. So you will find on the Gadgetron Online class um, tutorial for each lecture, and we will upload then, I think, the link to the video and maybe additional material at the end of the session, or maybe in the next day or next week. So for today, please go to courses day 1 lecture 3, and the tutorial is divided in 3 parts. So one is about the readout, the second is about car space, and the third is about images. And we won't have the time to do everything today, but I put everything so you can play with it. So I will start with the readout tutorial. I will present it, so you don't have to do it at the same time, because after you will have 1 hour to do it with a tutor. So please just follow me, and then you will have also the possibility, if you wish, to move to another room that we're gonna create, where you will have a tutor that presents the car space part. So it's basically how to link the Gadgetron to additional toolbox like BART, SIGBY, or Python package like PyGrapper. And the third tutorial is how to convert the data from the MRD format to Nifty. So it was made by Manon, and it's a beta version, but it's another way to interact with the images. So now I move to the readout. So basically, the Gadgetron is really useful for doing, I think, 2 things. So prototyping, in order to create a new sequence, and or I mean a new reconstruction, either with a new sequence or with an existing sequence, and to do the deployment. For the deployment, you will mostly need some C++ part, but for the prototyping, it's quite useful to do it with a simple language like MATLAB or Python. So I'm not really a Python user, I'm more a MATLAB user. So I have some, I do not know everything about Python, but what we're gonna do is quite simple. And it's in Python is also really popular for doing image processing using ITK or VTK library, or for doing machine learning using TensorFlow or Keras. So for doing the tutorial, you need to install 2 components. So the Gadgetron using the ppa install, and Python Gadgetron using this command. And there is additional package that can be that will be useful for the second part on car space. So I'm assuming that I'm assuming that everybody has done the installation, but in case you can follow and do it later. We find that if you're working with the WSL on Windows, you need a client to get the Python output. So this is the link to these tools that fix the thing. I will use for the demo API sequence from the CMR sequence. So it's only, so there's 2 data sets, one fully sample and one with graph acceleration. The data has been converted using Siemens to SMRND. We will not discuss about data conversion. This will be the topics of day 2. In order to download the data, you can follow this link, and I think it also has been posted on the Slack account. So the objective is to learn how to do a Python gadget from scratch, and to create the XML configuration and to do data manipulation. And then for the second part is to become familiar with the Cartesian reconstruction pipeline and to call, for instance, BART, SIGPy. So there is some redundancy with the presentation of Christopher, but it's more to go to practice. So this is a typical Python gadget. So you need to import some library, NumPy, Gadgetron, MRD, and a gadget is just a function that receive connection. So the Gadgetron, you can see it as a tube that receive message, and each time a message go to a gadget, you need to open the message, read it. You can interact with the message, but it's not really mandatory. And the mission of the gadget is in a way to send the message to the next gadget. In order to do that in Python, you just loop over the connection that are coming. So we will define something like acquisition, but it could be readout or images that will loop over connection, and you can do something and send it to the next gadget. So in order to do it, I will create a folder here. I will do this way, and you go to the folder, and then we're gonna create the first gadget. So I write, and I copy and paste the following line. Save the file. I will just print some output in the loop. So each time I receive a readout, we'll see so far, so good. Now, in order to call the gadget, we need to define the rider and writer, like Christopher tell us. Yep. And we're gonna create a new configuration file and copy and paste the writer and reader. So we have two files, and call our gadget using the following line. So you have block here, stream, and then you need to call the file, my first Python gadget.py, so you don't have to write .py, and the name of the function, which is below. Empty Python gadget is the target, and the language is Python. Okay. Close this one. Need to save it. Okay. So there's no compilation and installation. And now we need two terminals. So you can do, the terminal need to be in the same folder. That's important. In one, you just call the Gadgetron. And in the other one, we're gonna use the client that mimic the MRI. So the command line is Gadgetron ASMR MADI client -f the path to the data, minus C with uppercase to the XML configuration file. So, yep. And I think the data should be, yep, many things. Day 1, lecture 3 should work. Yeah. So be careful that you're using FID, MB0, GP0. So it's a fully sampled API data. Yep. Let's go. And you see the data are sent to the server, and you can see the print. So now what we can do is just create a counter that will show the number of readout. So in the function, we define a global variable And each time we go through the loop, we just increase the number. Yep. We save the file and do it again. And you can see that I have 3,565 readout because I have something like 3 repetition, 12 slices. And if we do for the mar, we should see this number. So let's continue. I would like to print the shape of the readout. So I use the command np shape. So this is the equivalent of size in MATLAB. And to get the data, I just type acquisition.data. Save it. And so we can see I have 12 channel and 246 point in the right readout direction. So then we can display some information like the active channel or the scan counter, which is actually exactly the same as what I did before, but it's really coded into the data. So I will comment this thing. Hop. Hop. And you can see the scan counter and the active channel for each readout. What is important is to associate the readout with the encoding location. So every encoding direction is indicated. It's something called IDX. So we have the slice number, the repetition number, the position in KY with K-space encoded step 1, in KZ in K-space encoded step 2. So we can print it. Yep. I will comment the other part. And you can see that my last readout is slice 11 repetition 2, going from 0 to 11, 0 to 2. And I have the encoding duration along Y here, and the segment. So in EPI, you have positive and negative readout that are indicating in the segment. So now we're going to use something called the connection filter. So we can filter the readout really simply and just put it at the beginning of the function in order to work on some specific data. So now let's say I want to keep only repetition 1. I just say that I just mention the encoding I want to keep. And then if we look at it, you will see that if I don't go too much up, I have only repetition 1 coming in my Python gadget for all the slices. Yep. You can precise. I just want to keep slice 0. Yep. And you can also use specific tag related to the acquisition if you want to keep only the reverse readout. And you can see now all the segments are set to 1. So as an exercise, you can use the flag ASEQ with parallel calibration. So when you have undersampling, there is some ACS that are required at the beginning of the acquisition. If you use this data set, you will get nothing because this is fully sampled. But if you use the second data set with GRAPPA2 acceleration, you will see 24 readout coming for each acquisition plus some fast correction data. So now I will just show you an example how to use matplotlib to show some information. So we'll use this flag, which is the fast correction for the API. Yep. So just a reminder, if you do you see my screen? Yeah. If you do a flash images, you will do one excitation per line. So, and if you do API, I mean single shot API, you will do you will cover the cast space in one shot, and you use some blip to move in y direction, and so the readout are not in the same way, and you need to correct for gradient perfection. And on the Siemens CPI, you will acquire 3 lines more, exactly not in the same way, at the beginning of each repetition. So this is additional data you will see. Okay, so if I put the flag, sorry, here, and only look at the slice 0, you will see for repetition 0 or 1, 3 line, 3 line, and then 3 line. We can use matplotlib to show them. Yep. And I want to show the reverse line in red and the positive line in blue, and I will show the FID. I mean the magnitude of the FID. So we'll write. I only picking the first channel. I do squeeze like in MATLAB and apps to get the magnitude. And I copy the line here below. So if it's reverse, it's red, otherwise it's blue. And every 3 line, I do the plot. Okay. So it's a pop-up come up, and if you close it, the reco continue, and you can see the next repetition and the last repetition and the reco end. So this way of working is compatible with inline processing at the scanner. And with the new Python interface that Christopher implements, you can also debug in Python, in Spider, and in Jupyter Notebook. So I mean, you can just block your data flow and play with it and launch it again and send back the image to the scanner. Well, in practice, it's better to try to work with your data a bit before, but you can do it directly at the scanner if you have the scanner time. So all the correction, for instance, for API has already been implemented in C++, but you are free to redo it. So the last exercise is to do a simple buffering example. So you need to know the size of the cache space. And in order to do that, you have to catch information that are located in the flexible header or the MRD header, and you put it as the information are quite general. You only need to catch it once, not for all readout, and you will need to have the matrix size, the number of slices, number of repetition, and then you can do an allocation. So you just allocate a big matrix. The only thing to worry is you use complex type, and then you can catch the encoding position and copy your data into the buffer. So I will let you do it as an exercise. And I want to show you, before breaking the room, a last example with more complex data. So here I'm running some 3D VSSFP sequence with undersampling in Y and Z direction. The sequence has a respiratory navigator and is ECG trigger. And you can get all this information in the Gadgetron and show up. So I just made some plot. Yep. Yeah, I think I have to report something to Christopher. It's not working. Try again. Yep. It's working. And you will see, so figure 2 is the ECG that are transferred. Figure 1 is the navigation. So this is only the upper phase. And figure 3 is the mask of the gas space in KY and KZ direction. And I'm just located at the beginning of the chain. So I'm just receiving plenty of readout, and I plotting the waveform, so that got the ECG, the gas space position, and the navigation data. And you can interact with it and sort it, and then do the reconstruction. So this is just an example. So the data are available in the folder, so you can try to redo it, and I can share the code next week if you wish. Just need to kill it. So now we're gonna split the room.